Hey, welcome to another video. Today we're going to talk about extrema, local or relative and absolute extrema. What that means is local maxes, local mins, absolute maxes, absolute mins. Talking about high points and low points of our graph. So let me explain the difference between local max and min or relative max and min and absolute. And then we'll just go through some examples and learn exactly how to determine local max and min through graphs. We won't be able to do it very well with algebraic expressions because we pretty much need calculus to do that, and something called a derivative and a horizontal tangent and some things that we are not ready for. But getting an idea about what they mean now is important so that when we find them later in calculus, you'll understand what we're finding. So what a local or a relative maximum or minimum means is that in an open interval, a little neighborhood of your graph, you have a high point or a low point. That's pretty much what a local or relative max and min mean. The definition of it is that on this open interval, we have this value that is higher or equal to all the other values around it. For a little neighborhood, not the entire graph, but just a little neighborhood of an open interval of the x-axis. So the value c would be called a local max. One thing to understand right now, when you're finding a local max or local min or absolute max or absolute min, the output value is the maximum or minimum. It occurs at a point, x comma that output, x comma the local max, x comma the local min, or absolute max, absolute min. But the output value itself is what we're talking about as far as a local maximum. And that should make sense. The maximum output would be an output value, and the absolute maximum output would be an output value again. So keep that in mind. We're finding the value of the output at a certain x value for our input. So an easier way to remember that, as far as what a local max or local min is, where to look for it, a local maximum is going to generally occur, like 99% of the time, it's going to generally occur where we change, think about this, where we change from increasing to decreasing. On that change, remember that the increasing is open and the decreasing is open, and where they change, we didn't include that point on increasing or decreasing. Well, that point itself is where the change happens. That point itself is a local max or local min. So when we change from increasing to decreasing, we're going to have a little peak there. That peak is our local maximum, or where that local maximum occurs. So we are going to generally look where a function changes from increasing to decreasing, and that's going to give us a relative or a local maximum, a neighborhood of points, this open interval where we have one value higher than all the other ones, higher than or equal to all the ones around it. Likewise, for a local or relative min, we're going to have this value that's lower than or less than or equal to all the other values around it on an open interval of points. This little neighborhood. Generally, that happens where a function changes from decreasing to increasing. Well, we're going to have a little trough there. So we've fallen and then we've changed from decreasing to increasing. Well, where that change occurs, where you're no longer decreasing and you're not starting to increase yet, that little point, that's where your local minimum is going to occur. A couple things to note about this. You do not have to have local maxes or local mins on any of your graphs. You also don't have to have absolute max and min on any of your graphs, but where they occur is going to be a change from increasing to decreasing, most likely, or decreasing to increasing for local minimum. Why I say most likely, there are some cases where we have constants that this can come into play. So I need you to understand that. Also, you can have more than one place where the same local maximum occurs. You can also have more than one place where the same absolute maximum occurs, or likewise same minimum. So the main idea is look for areas of your graph where you're changing from increasing to decreasing for maxes and decreasing to increasing for mins as far as relative or local max and min. Absolute max or min just means the highest and lowest point that your graph attains. So the absolute maximum is going to be this thing that you never get a value higher than that as an output. Absolute min is going to be this value that you never get a value lower than that on your graph as far as an output is concerned. So a few things to note. You don't have to get these either. They could not be non-existent on your graphs, but where they occur, you're going to get you're going to get this actual physical point that you do not attain a value higher than that. I need to make a note that every closed interval, brackets, every closed interval will guarantee you that you have an absolute max and an absolute min. That would be a closed continuous, no gaps, no jumps, no separating things there, no asymptotes. Then you can guarantee that you have an absolute max and min. Without that condition, you cannot guarantee it. So every closed interval that's continuous is going to have both an absolute max and min. I'm going to put the word continuous up here. I'm going to spell it right. So every closed continuous interval is going to have an absolute max and min. We're going to try these right now with one thing I need to make sure. The last thing is that local or relative maxes cannot occur at endpoints. Absolute maxes and mins can occur at endpoints. So, one last time all the way through, what local means is on a neighborhood. So on this little thing, you've changed from increasing to decreasing, local max, or decreasing to increasing, local min. You have a peak or you have a trough on your graph somewhere in a little neighborhood of points. Endpoints don't qualify. Because it's defined as an open interval, your endpoint is not on an open interval. Your endpoint is on a closed interval. You can't get past that endpoint to determine whether you've changed from increasing to decreasing or decreasing to increasing. You don't have that point being higher than all the points around it because there's no neighborhood to look at. And so we do not include endpoints for local maxes or local mins. Absolute maxes and mins, that's the highest point or lowest point in your graph. Every closed continuous interval is going to have that. And we can't allow endpoints because we're just looking for the highest value attained. That's the idea. Keep in mind that all these things are the output value. They occur at a point. And so the point itself is not really a local max, local min, absolute max, absolute min. It's just where that occurs. The output value is the maximum minimum we're looking for. So we're going to do however many that is, looks like 6 examples. I'm just going to go through what the local max, local min, absolute max, absolute min is, what they are. I'm going to change this last one to make it work for us and talk about how the absolute max and min, the absolute max or min value can occur at more than one place. We have to define that. So here we go. As far as a local max is concerned, when we look for a local max, we are looking for a point where our function has in general changed from increasing to decreasing, or a neighborhood of the x-axis, a little interval of x-axis, we have a high point, a little peak. So that right there, this graph changes from increasing to decreasing. It has a little peak in this neighborhood of points on the x-axis. That's the highest point that there is. So our local maximum is not 2. It's not 2, 4. The local maximum is 4. It occurs at the point 2, 4. But you see the difference. You should see the difference. The maximum value in that little neighborhood is 4. That is what we're talking about. It just occurs at the point 2, 4. Likewise, there is a local minimum or a relative minimum. You can say either one. The local minimum, well, wherever we change from decreasing to increasing, wherever we have a little trough, wherever we have a neighborhood of points where we have a smallest point, that would be right here. So we're decreasing, we're increasing. Where that change happens, negative 2, 1, that's where our local minimum is. So the minimum value is 2. It occurs at the point negative 1, 2. This is not a local minimum. And this is not a local maximum. The reason why is because there's no neighborhood around it. It stops right there. And you go, well, what about what's next? I don't know what's next. So you can't say that it's changing from decreasing to increasing because you don't know what's next. You can't say it's on an open interval. So we can't say that that's the smallest point on the open interval to define a local max or min. So it might seem like a nuance, but we can't include our endpoints for local max or relative min. We can do it for absolute max or min. And so when we look at the absolute max, what we're looking for is the highest value attained by your function. Notice one thing about it. Can it occur at something that's also a local max? Yes. Does it have to? No. So in general, we look at our local maxes and we look at our endpoints, and whatever's the highest out of those, that's your absolute max. So we look here at, is that the highest value for, or is my endpoint the highest value? Is this endpoint the highest value? So I'm looking at output, output, output. Oh, that's the highest output. That right there says that this endpoint is where my absolute maximum occurs. I'm being very specific on my wording here. The absolute maximum is 5. Where it occurs is -4, 5. Can they be at local maxes? Yes. Do they have to be? No, they can be at endpoints. Locals cannot be endpoints. Absolutes can. Absolute minimum. Let's see, the lowest value attained by our graph. Let's look at our outputs. 5, 2, 4, 1. Okay, that's the smallest output we have. It doesn't go any lower than that. My local minimum, it has a value of 2 right in this neighborhood. My absolute minimum has a value of 1. It occurs at an endpoint. That is okay. It's 1 at the 0.51. Yeah, this should be making sense to you at this point. No pun intended. That the value of the output is our max or min, and where it occurs is our point. So let's look at the next one. So we're going to go up here. The next one, if we look at that, that is a continuous function on a closed interval. Do you see it? Same thing here. There's no gaps. There's no missing points like we have in these. There's no asymptotes that we're trying to we can't cross over. This graph right here is going to have an absolute max and an absolute min. That doesn't guarantee we have local maxes or mins, but a closed interval with a continuous curve is going to guarantee that we have a highest value and a lowest value. It's got to be that way. So let's go ahead and identify our local max, local min first, and then our absolute max and min. So our local max, we're looking at our graph and seeing where we change from increasing to decreasing. So here I'm decreasing, here I'm increasing, here I'm okay, so I'm changing from increasing to decreasing. That's going to create a peak and neighborhood where we have a high point. The local max here, right there, is 5 at the point 3, 5. We also have a local min. So where we change from decreasing to increasing. Okay, we've decreased. Okay, now we're increasing. That point right there, where we change from decreasing to increasing, it's a little trough. That local minimum is -1. That's our output value at the point -1, -1. That's where that occurs. We never include endpoints for local max or min. So this not included, that cannot be included because we don't have an open interval. Absolute max or min. So now we're looking just for the highest value that occurs. So the highest output, our outputs are 2, -1, 0, and 5. The highest of those values occurs actually at that local max. So the absolute max is also 5 at 3, 5, but for a different reason than this. So the local max is a change, where we change from increasing to decreasing, or in a neighborhood of points. We have a high point. It does not have to be the highest point in your graph, does it? Because this is still a local max, but it's not the highest point. This is a local max for the same reason this one is. It's a change from increasing to decreasing. In a little open interval, it's the high point. Just looking at, like when you zoom in, oh, that's a little peak right there. But it's not the highest point. It's not the highest point here. It is also the highest point here. So the local is just a zoomed in idea, and absolute is the big picture. So big picture, the 5 is also the highest value we ever attain. It just so happens that it's also occurring at a local max in this case, but at an endpoint in this case. Absolute min, same thing. The absolute minimum here, let's see, 2, 5, 0, -1. The -1 is the lowest value that we get. It happens to occur at a local minimum and not an endpoint here. So you can have absolute max and min that are the same as other local max and min or at endpoints. Generally, that's where they're going to occur on continuous curves, is absolute max or min is going to occur at a local or at an endpoint. And using calculus, when we get there for continuous differentiable curves, we look at that. We look at the local max or min, critical points give us those, and we look at endpoints and determine what's our absolute maximum or minimum. All right, I want to go on to this one, then this one, then this one, and that one. So we're moving over here. Now, we're missing some points. That's what those little open circles mean. They say you get close to it, but then we're just removing one little point, like a removable discontinuity. We say a discontinuity. So this is no longer a continuous function, which means that this whole, hey, every closed interval is going to have one of these, that's true if we have a continuous function. And we're going to see how removing that point really affects a lot of what we're going to do. So let's see. Do we have a point where we have changed from increasing to decreasing? Well, we're increasing, decreasing. So at that point, if there was a point there, we would have a local max. We would have a peak. We'd say, hey, in the neighborhood around this little open interval, we have a high point. This value is higher than anything around it. But if I take that point out and say, oh, that's no longer there, well, then we will still increase forever here. This is still increasing. It never stops increasing. This is decreasing. It never stops. Well, it never actually has a point where you're not decreasing on this open interval. So we can't actually change. We can't have a point where it's neither increasing nor decreasing. Everything up to the 3 is increasing. Everything after the 3 on the x-axis is decreasing. Where that value that we changes, it has been removed. Therefore, we don't have an actual point on an open interval that's higher than anything else. They say, this is the highest point. We don't have that. And so we do not have a local max here. We would, but we took it away. So there's none. We also have no local minimum or relative minimum. And it's not just because this point is gone, it's because we never change from decreasing to increasing. Endpoints can't be included in those anyhow, and there's not even an endpoint there. So we're always decreasing here. There's no value that's the literal lowest in the neighborhood of points, an open interval. That doesn't occur with endpoints in general, or even at this open missing point, because you can always get a little bit lower, a little bit lower, a little bit lower. There's no solid point that's the lowest in a neighborhood. Same thing here, endpoint, we failed to be on a neighborhood of open interval. So there's no local max, there's also no local minimum. Is there an absolute maximum? No. For the same reason that there's no local max here, there's no actual physical point that you say, this is the highest I can attain. You can get like 4.9, can't you? You get 3, comma, or what, close to 3, comma 4.9, or 4.999, or 4.9999, but you never get an actual highest value. Because we're missing that 5, you never get to the 5 for the output, and so we don't have an absolute max. Do we have an absolute min? Sure we do. This doesn't continue to go down. This kind of fizzles out as we approach a height of 2. So x is 6, but height is 2. But we do have a lowest point of -3 on that endpoint. And that occurs at 0, -3. So notice you can still have some absolute max and min. If we don't have a closed continuous interval that's closed and a continuous curve on that, but you can still have them. It just doesn't guarantee it anymore. So yeah, no local max, there's no point there. No local min, we have nowhere where we change from decreasing to increasing. Absolute max, again, there's no point. Absolute min, okay, we can now include that endpoint. That's the lowest value that we have. Let's go, you know what, let's do that one. So do we have a local max? Think for yourself. Is there a point, defined point, not open, where we change from increasing to decreasing? We're on an open interval, little neighborhood, we have a high point. Yeah, we have one right there. So the local maximum is 4. It occurs at the point 2, 4. Do we have a local, and there's only one of them, do we have a local minimum? Yeah, we have a point where we've changed from decreasing to increasing. There's a little trough here. We know that in the neighborhood around this point, that's the lowest spot, has a height of 1 at the point -1, 1. Do we have an absolute maximum? Sure we do. We have a high point on this graph. Right there at that local max, that's also the highest value attained on this graph. So we'd have an absolute max of 4 at the point 2, 4, just like our local max, but for a different reason. It's just the highest point that we get. Do we have an absolute min? Well, no. No, this graph decreases, increases, and decreases, and it keeps on decreasing forever and ever and ever. As x approaches whatever that vertical asymptote is, this graph approaches negative infinity. So we're not going to say negative infinity is the absolute max, even though that's where the limit as we approach the x value would go. The limit's value would say, yes, it goes to negative infinity. A limit is as we get closer and closer to something on the x-axis, our graph approaches something on the y-axis. That's basically what a limit does, a value from the y-axis. Here we don't have an actual value though. So an absolute max has to be a point, a value that we attain that happens to be the lowest value on the graph. There's none here. We wouldn't put negative infinity. We wouldn't do that. All right, moving forward, can you have more than one local maximum and more than one local minimum? Absolutely you can. So here, where we look at this, we're decreasing and then increasing. Okay, that's a local minimum. We're increasing and then decreasing. Okay, that's a local maximum. We're decreasing and then increasing. That's a different local minimum. It's okay to have several local mins and local maxes because we're looking at individual little neighborhoods, individual little open intervals. So you could have a graph that just does this all day long, and you could have hundreds of local maxes and hundreds of local minimums. They could even occur at the same value. Like, well, sine and cosine, when we get there, we're going to see they have an infinite number of local maxes. Every pi or pi over 2 intervals, you're going to get this, oh, there's another peak. Oh, there's another trough. There's another peak. There's another trough, like a little roller coaster over and over and over. And they get the same height again and again. You just have a different local max and local min at every single one of those x values. So our local max here, it changed from increasing to decreasing right there. In that open interval, the highest value is 5. And it occurs at the point 0.05. Local minimum, we have 2. So we have 1 where we change from decreasing to increasing here. Careful, the height is 0. That's the local minimum. It occurs at -2, 0. We have another one, decreasing, increasing local minimum. We have a height of 1 at the point 3, 1. So we certainly can have multiple local maxes because they're neighborhood oriented. They're just a little open interval around a certain point where that point is the highest point in that neighborhood. Absolute max, what do you think? Absolute max. Absolute max? No. Absolute max? No. Oh, it goes to infinity. So as we're approaching whatever this number is on the x-axis, our graph is going to positive infinity. For that reason, we have no absolute max. We do have an absolute minimum. So we're looking at the output values, 3, 5, 1, 0. 0 is the lowest value that's attained by this function. Therefore, that's the absolute minimum. At this point, this should be really making sense. Like, okay, I understand that the output value is the local max, local min, absolute min. I should be understanding that on a continuous curve, on a closed interval, has to have a highest and lowest point. As soon as I mess with that, start taking points out, start having non-closed intervals like these, well, then we start removing that necessity. We start looking at just, okay, is there a highest point? Is there a lowest point? It could occur at a local max or min, or it could occur at an endpoint. Local max and min cannot occur at endpoints because they have to be based on open intervals, but we can have more than one of them. You will only have one absolute max and min. You can have many different local max and local mins. Let's check out one more. Maybe you see it. You should be seeing that there is no local max here. Even though we change from increasing to decreasing, that point's removed. There's no local min here. Even though we change from decreasing to increasing, the point's been removed. There's no absolute max. Highest point, there is none. It gets closer and closer to 5, but never gets there. Absolute min, there is none. It gets closer and closer to whatever this height is, but it never actually achieves that value. You can get closer and closer, but never gets there. Now let me change it just a little, so there's nothing on this graph. Let me change it a little bit. Let's put that point there. Let's say that's -4, 5. Does this graph have a local max now? Yes. The local maximum is 5. It occurs at the point 5, 5. Does it have a local minimum? No. That point's still missing. A local Let's see, absolute minimum. Nope, this point's still missing. This is not the lowest point. It does get lower than that, but it never achieves the lowest point. Does it have an absolute max? Yes, and an absolute maximum can occur at more than one x value because you need to understand what an absolute max is. An absolute max just says, what's the highest output you attain? Well, the highest output I attain is 5. Now, it occurs at more than one place, but that is the highest value this graph gets. So an absolute max here it's 5. That's the highest value. It occurs at 2 different places. At 5, 5, and negative 4, 5. So hopefully that explains it to you, what local or relative max and min are, how they're defined, why it's important that you can't include endpoints because of that open idea, how you can have more than one of them at different values. That's okay, just every peak, every trough that we have that's defined, has a defined point. And how absolute max and min is just the highest value on our graph. It can occur at endpoints or it can occur at local max and min. And it can occur at more than one place, so no problem. So hopefully that makes sense to you. I'm going to come back and talk about average rate of change in just a little bit.